I just put this up so that you can kind of digest a little bit of some of the thought process behind this discussion group and where we want to focus on. I don't need to read through it, but it's kind of as you're finding your seat. The main idea is that for these discussion groups, we want to look at different aspects of the process, right? And then different the machine technologies, materials technologies, but then what is important in a printed part that's going to drive our processes moving forward, that's going to drive us as a community towards here's what we mean by a good printed part, here's what we mean by a successful design. And so I think we've organized these groups so that we'll have some time in a smaller session to have some open discussion about where we stand, maybe some of your experiences with the part design, with different, maybe with some of your customers, maybe yourself, on that, and we'll be taking notes on that. There will be a report out at the end with some of the notes from this group, and then also the other groups that come in for this discussion, and then the different discussion groups that are part of this one. So I guess one thing that would be helpful to start out with is maybe to kind of just, if we could briefly go around and just, talk about some of the parts that you're experiencing usage of, maybe that you're doing, maybe that some of your customers are working with, some of the people you interact with. So what type of parts are you all working with?
Like start with you. Work in aerospace. So big challenge is how do you actually get production parts? How do you qualify it? How do you verify it? So we're very limited in what we've done on actual flying parts. So we do a lot more tools. That's one of our main focuses. But there's still requirements how you use a tool. Make sure it performs how you want it to.
Okay. So both production parts and tooling.
Yeah, most of it's tooling, and then of course we also have engineering models, wind tunnel models.
Now, can you say anything towards the specific application of some of those production parts, or are those kind of?
So for any sort of program that's not a developmental program, so you look at non-structural parts, non-flight critical, so that's things like knobs, brackets, bumpers, covers, things that if it fails, the plane's not going to go out of the sky.
Okay.
And a lot of it's on the sustainment side of things, where there's more of a push from the customer because the cost for replacement parts is so astronomical sometimes because tools can be damaged or destroyed, so there's no good way, no cost-effective way to get the traditional parts. So additive is a good answer to get you close to what the production part quality would be.
Yeah, try to deal with locomotives, and we do parts and tooling, but the parts are really the important things we're working on right now. Tooling is fairly easy compared to printed parts, and we have a production vehicle that has 3D printed parts on it now. We've got maybe 15 produced to date, something like that, and these parts are, I wouldn't consider them critical structural parts. They're kind of bolt-on parts that have a shape. That's the wheel housings and the key panels of the production ollie. And that's been fairly straightforward for that part. They're heavy though. It's kind of just more of a novelty of having 3D printed parts on there than really using it as a structure. And so we've been working on this 3D printed ollie as another design, and that we have that as a lower structure and an upper structure. We're still in design trades for final material for that, but the material we're using right now is performing very well. We've done a full-scale structural test of that. We've printed at least 4 of them, printed and machined. One was a full-scale structural test. One we've done a full vehicle crash test on just last week, and So, and another one's going to be a driving version, so that's being assembled now. So that's the three main ones. We've got one that's still on the printer being machined, and then we have one that I think they shipped off to display the model. So, I don't know what else to say about it. I mean, I would answer questions if people have them, but it performed fairly well. We modeled the material just as an orthotropic material in a fairly simple FEA model, and it behaved fairly well. I mean, as far as correlating the model to the full-scale structural test that we were able to do. But material characterization we're doing on the panel, coupon level, and we did some testing with carbon fiber ABS a year ago in some subcomponent tests, the complex subcomponents. So that's how we sort of built our database of properties of printed parts.
So these parts that you're talking about, what's the base resin? What's the base material that's used?
Well, we started with carbon fiber ABS, and right now we're investigating several main chemistries, so carbon fiber polycarbonate and carbon fiber polyamide, primarily pH6 and pH66, as competing materials right now.
So is there any interaction between the material selection and the part design, or is it somewhat kind of separate? Or that you say, here's a part that needs this material, here's a part that needs that material?
So the design may change, or at least the as printed part design may change depending on the material due to like deformations. But we started with the design. That's just because of the speed that we were in development. The materials were coming sort of slower than the design. But yeah, we started with the design.
Is there any other end users? You know, we got Lockheed and Local Motors. Any other end users of whether it's tools or just trying to get a feel for who's all in the room? Everyone else is development side or making parts? Materials.
Yeah, materials.
Okay. So, I'm Andrew Bader from Additive Engineering Solutions, and we're a contract manufacturer of large-scale 3D printing. So we have the BAM system from Cincinnati, and we have a couple of those. We have machine centers, and mainly what we focus on is producing tools and molds in a variety of different materials. Room temp layups, autoclave tools. We do precast concrete molds. So that's most of what we do. Then the other 25%, I would say, is either some sort of large-scale mock-up or prototype. What Mike and I were discussing were some of the things that when we talk to our customers, and on the tool mold side, there's a lot of aerospace. We've talked to a few automotive companies. And there's the precast industry, which is starting to become pretty big. But some of the things that Mike and I talked about, what are people asking us, or what do they need from the results of our tools? How performance metrics and whatnot. And I kind of narrowed it down to there's material performance, and then there's the actual printing process, how that can benefit whatever the tool design we're doing. So I have things like, I just made a list of, people ask, what temperature can this material withstand? Pressures, like in an autoclave, or when you're putting tens of thousands of pounds of concrete into a large concrete mold. Surface finish, when you're using composites, sometimes there's Class A surface finishes you need, and do you need to put a coating on that, or can you, polish up the material itself without a need for a coating? Vacuum integrity is a big one. We're talking composites. If you're going to bag right to the surface of the tool, again, can you do it on the neat surface, or do you need a coating to ensure vacuum integrity? We get questions about longevity and durability. How many times can you pull a part off of a tool? I'll just keep going down. Dimensional tolerances. they know how an aluminum tool or a steel tool will look like 10 years from now. What's an ABS tool or an Altem tool or a PPS tool will look 10 years from now, just from being in environmental conditions over a 10-year period, right? Thermal conductivity, how long we put in an autoclave will it take to heat up, right? Repair and maintenance of these tools is a big one as well. You got different gap fillers and how close are those properties to the actual material properties, if you have a mismatch in some of those properties. So these are like just a handful of stuff that we get asked all the time, and it's difficult for us to answer a lot of those questions. We don't have all the resources, we don't have autoclaves in-house to test these kind of things, so we try to rely on customers who see this as a huge benefit to their company, and we try to get into prototyping, development tools where okay, we'll work with this material. How about we send it to you, we'll machine it, scan it. When you guys receive it, start putting it through whatever process you are doing, whether it's thermal cycling or actually laying up carbon fiber or fiberglass on it. But it's tough because there's only, let's just talk about autoclave tools, right? A lot of people want those. I keep trying to go to these room temp layups or maybe trim tools for composites are great, because I go into shops, I see aluminum everywhere and big beefy aluminum structures, and I think you can do away with that and work on ABS, cheaper materials. But regardless, everyone wants autoclave, and there's just so much there to have to deal with. Basically, that whole list of what I said all deals with autoclave tools.
How many people in the room deal with autoclave tooling with extruded deposition? It's a pretty big area of that. So
yeah,
and I feel like that's where a lot of our focus has been on the tooling side and the autoclave side, and then working up towards compression molding. But there's a lot of challenges with that. But I guess what do we miss when we focus on autoclave tooling? What are we kind of not addressing for other parts? Where we focus on these aspects. I know, Charlie, you have a different use case than that. Your quality metrics are going to be different than that. Some are going to be similar. I think dimensional tolerances are going to be cross-cutting across everything. And I think Roger, to your point earlier, that there's a lot of methods you can use to get those dimensional tolerances in a pretty good manner pretty quickly. So, from your perspective, do you work with a lot of the autoclave tooling, or are you more working with different types of the additive? I know you're not just on the FDM process. You have a lot of other things going on.
Yeah, we work on different topics, but we work on toolings, for composite toolings with stratesis. We're getting, the additive manufacturing tooling was much cheaper, much lighter, much better than the equivalent metallic for autoclave. But to get the shape right, to get the tolerance right, it took a long time, a lot of effort to work on this, to be able to predict warpage and to correct for warpage automatically. So this is what we've done. Our customers face a lot of problems with variability,
Okay.
with constant properties of materials.
So how do we account for variability?
You have to, variability not only for material, you have to capture it at least to know what it is, which machine, which software of the machine, which temperature of the day, what is the humidity, and so on and so forth. So a lot of variabilities that need to be captured. Tolerance, of course. We have also asked how can you compare 3D printed part to injected molded part. So how can you do functional prototyping with 3D printing? You have the visual prototyping, then you have functional prototyping before going to production. Versus, can you print something with 40% carbon beads to be equivalent to 20% carbon fiber, for instance? What is? Any
Yeah. I mean, beyond, so beyond that, I guess when you're talking about the functional prototypes, that kind of gets beyond just dimensional tolerances to strength.
No, we work mainly on final part performance, how it breaks, when it breaks and how it breaks, how to get allowance, for 3D printing measures.
Yeah. I think that kind of gets back to your point, Michael, about, how do we get something onto an aircraft, even if it's not, flight critical, there's still certification issues with that and strength. So.
I think that's the biggest struggle we see today from people who are
The being able to predict strength.
qualifications, certifications.
Yeah. I know that is a challenge that the entire composites community is, kind of trying to tackle.
Right.
Be able to predict strength because it ties back to variability in a lot of ways and being able to characterize that, being able to address it.
We are in the process of developing things to do virtual allowables for additive, like we do virtual allowables for composites, basically. So to reduce the test matrix to the strict minimum. This is some of the topics.
So I think another thing that we want to talk about is how do we, as a community, work together to try to address some of these topics. I mean, I think that we all want to be the one who solves it, right? But, there's a lot of, an area where the rising tide lifts all boats. How can we, as a group, work towards better design principles, better, I guess, strategies to be able to say, here is a methodology that works across our industry to say, this is the strength for your material. Do we have any thoughts on that?
Well, I think building databases, like our Acme project is something where once we publish that data, then other people can use it and they can see how someone's actually built a part out of this and qualified it to some extent. Going and looking at the quality control thing is something we're working on as part of that project, so that's really future work. But the value proposition is, for us, is this design iteration. Like I mentioned, the 5 chassis that we produced, but every one was a little bit different. Like we kept optimizing the design as we went along. Like after we finished the structural test, we made some changes, and even the design guys, like they wanted to make some changes just for how it looked. And we were able to implement the changes and reprint it and model it. And so, there's value there. It's hard to quantify that, but it's definitely what we see as a value is that rapid design cycle that you can achieve by using this process in the product development, at least in the product development, and even for mass customization was the other sort of angle that our company was looking at for the highway car program that was a couple years ago was, once we demonstrate this in the low-speed electric vehicle, we then get it to the point where we can look at highway certification. So I see that as a value proposition.
Yeah, and I think you bring up a great point about the balance between commodity and customized.
Yeah.
Is that, one of the benefits of additive manufacturing is that every part can be different. And, with variability, maybe every part is different, whether you like it or not. But, but we can, but there's uses that say, okay, well, additive manufacturing makes sense to make a commodity level of these things. If we can print out, 1,000 of them, then of the same thing, then this makes no sense. But I guess how do we, I don't know, do you guys address?
Yeah, so, we work with tons of different people, and it's funny, we might be doing one project with one customer, and it's, maybe on one of these 10 things I said, and then another customer is doing another project on one of these 10 things, and they might share only so much back with us, and say with the other customer, and you've got different pockets of different people out there who are working on different areas, and if it was somewhat shared to some degree, I think it could, move a lot faster forward. But, people want to hold some of that information to themselves, and it's tough to get them to release some of that information. So we would love to be able to solve half these things on our list that, you know, customers always ask us. And I think we could a lot faster if people got together and were able to do that. You know, these IACME projects are great because, you know, you do get, we're on one as well, and it's, I don't know, probably 5 total different aerospace folks in the supply chain. Working on that together is huge, and they are solving, they're going through probably 3 or 4 of these things on my list. And once that gets done, I mean, that's just one data point, though. That's just one project. I mean, you can obviously move just one project, but it's a start. So somehow collaborating together seems to me the fastest way to get there, really.
I have a question, because I cannot say I have an answer. I'm dealing daily with metals, right? And dealing with metals, we have 3D standards, like the ISO standards. My question for the group, do we have something like that on the carbon fiber, 3D printed type materials? Something that we're working on in the community, or?
Yeah. So I think one of the challenges is that we have a lot of standards, right? If you have a lot of standards that you don't have any, you know, there's a lot of people that want to say, here's how we.
Well, there is a ASTM committee, the F42 committee, that's working on establishing what the standards need to be for additive, because the process is so different from most of the rest of the things. I mean, we can use some of the data that we use in traditional testing that we usually use for injection molding or traditional extrusion, but there have to be additional ones put with that. In addition to that, I would say one of the very important things, the first project that was funded by American Makes was the material characterization program for 1995. And in fact, they're still carrying that program on, but it was seen as so important. They got all of the aerospace manufacturers to actually work together, which is somewhat difficult. But the idea was there was so much value in characterizing that material so that everybody could use it, that it was worth it to all of them, because otherwise we never get this industry off the ground. So that's something we might want to look at, possibly collaboration type thing with American Makes and IACME to be able to utilize that kind of data.
Yeah.
Because it works for both sides.
Yeah, I mean, I think that's an area where, you know, that kind of pre-competitive collaboration makes a lot of sense. And the characterizing, I guess if you're a material supplier, you don't really count that as pre-competitive because it's competitive for your material. But, you know, some of those things that, you know, being able to arrive at those values that everybody can share and say this makes a lot of sense.
This is, it makes more sense even for the machine manufacturers, because it could still be characterized across some machines just to validate. I don't think, in some cases, you know, at least when you talk about large scale extrusion, that we're going to see huge differences between deposition from a Cincinnati dam system versus a third LCM system. There'll be some, but I don't think it's going to be as big as, you know, the difference between one person's carbon fiber yes to another system.
Yeah.
And to that, you know, processing standards are really tough. You know, Mike has a BAM, we have a BAM. He might run a certain material hotter than we do, and we all saw, you know, B2B layer adhesion can differ just from how hot you run, or from your tamping device, whether you're using something that's tamping or rolling. You probably get different, you know, characteristics of your part. You know, if we go 50 degrees hotter than Mike does, or whatnot, and the issue is, you know, we're constantly, I know everyone in this field is constantly improving the technology to make, you know, the machines, you know, deposit faster or larger. You know, when we were starting off at a 0.3-inch bead, now you're going up to a 1-inch bead. What does that do? Do all the work that we worked on for that past year, do we throw that out the window? Can we tell customers going forward, you know, well, we're printing with this bead, which is 3 times larger than the last bead. I'm not so sure if that, you know, that data from a year ago is still relevant now. So when you're constantly improving the technology, how does that change what you've already worked on too?
Okay, so you're looking at, I don't know, when injection molding was started from the 50s or something like that. I mean, it's like thinking back then, people thinking, how do we design standards for this? But we have no clue what we're doing with it, right? We're just learning as we go, right? So I think a lot of it's just going to be a matter of time, until a lot of the different techniques, a lot of the different methods, some of them are going to end, some of them are not going to go anywhere, others are going to continue, and eventually it's going to be kind of a common thing that everybody does in a certain way, right? I just think it's a matter of time.
Yeah, but I think another thing is that looking back 50 years, I've mentioned this, that computing capabilities increased billionfold over that time. How does simulation fit into the standards? Is it something that is integrated into standards? Is it something that kind of supports that? The landscape is a little different than what we had at that point. I wasn't around, so I can't tell you for sure. But there's how do we tie in the simulation capabilities? I mean, obviously that's the main focus of ours, but is that something that is critical to the development of standards? Is it something that's kind of off to the side? Is it kind of an internal thing?
I think simulation would play a huge role, just what I was saying. If I said, hey, we're going from a 0.3-inch bead to a 1-inch bead, let's input that and see, does that really change things drastically? Or, we went from a mechanical tamper and go to a roller, how does that change? And if you can put that into software instead of having to recharacterize everything you did, to physically recharacterize it all and send it out to labs to have it tested, I think that would be huge.
So I want to touch on another point here. It's I'm not materials manufacturing, so I'll leave that when we talk about materials. But one of the things we want to do is be able to prototype tooling quicker, injection molding tooling quicker, because every day we have customers that want to try our materials, and they're not willing to invest however many thousands of dollars in a prototype tool to just get a quick proof of concept, right? So we'll be looking at this, and scale-wise, and you think extrusion deposition is probably too big, right? Because you're talking about fine details in molding. But on the other hand, you get the benefits of the properties that come with the extrusion deposition, because now you have a fiber field system, for example, that you can put directionality and a certain level of anisotropy that you want. You can design around that, because you can design the features of the mold that you want to be stiffer or not based on that. That's huge, right? So how do you marry those two things together, right? That to me is really powerful, not only from the material manufacturing point of view, but also our customers who do a lot of prototyping, for them being able to take advantage of this. Because if you think about it, the other types of 3D printing technologies are useful, but at least to my knowledge, they don't give you the full range of property beauty that you can get from something like this. That to me is where the big CTQ for me would be, how do we make that more mainstream? That ability to really make this at a smaller scale, but using those same properties, right?
Scaling.
Yeah.
We have about a couple minutes more before we go to. What else?
I got a question. So from your previous experience on different projects, is there, have you kind of, is there any relation between, let's say, the smallest feature that is worth it to make in a printed part compared, for instance, to the big geometry? Is there any metrics on that end? For instance, for a mold, you can definitely machine any complex shape, but might not be the right solution to go with 3D printing for certain features. So is there some kind of metrics?
I mean, we print anywhere from a 0.3-inch wide to a 1-inch wide bead, 100 thou thick to a 1/4-inch thick bead. So high fidelity in details is not easy. And, typically what we do is on the machine side, we try to machine the detail in there.
Yeah.
But even still, we try not to machine past, a 1 bead wall. Because we talked about, bead to bead compaction, we got the 2 beads together, you machine down for that first one, you'll start, going into the second beat, and in between the two is where you'll find porosity. So we've had, several projects that we quoted that, you see some kind of cavity that they need machined out, and you're going to go a few layers in or a few walls down. We just, especially if it's like a high temperature, if it's something like an ABS, there's methods to, after that's done, to repair it or fill in any, gaps or porosity. But, we try to stray away from a lot of the high detail because of that. And I think, some solutions to that is better bead-to-bead compaction, where, if you make a wall and you take a cross-section of it, sometimes you can see the holes in between, each intersection of beads. And, whether that's better tamping methods, or, maybe you're filling it out more and you're extruding more and slower, so it fills it out a little bit better. But you can talk to Clark about that. We just ran a plethora of tests in-house, and then, took cross-sections of them and see how they looked.
Yeah.
But yeah, that's a good question.
So even just like the part homogeneity, across the beads is another CTQ that we can address that have, that better.
Yeah, and the things I said, customers are asking about, surface finish, and they don't know the details of the printing process or whatnot, but I can tell them, if we do that, that's going to open up issues. Here's how we can get around it, or we can't get around it, where we are currently with the technology. So,
One thing to add, with this technology, it's a unique opportunity out from the material side of things, and a lot of times we're talking to people that don't know anything about plastics, have never interacted with it. It's a learning opportunity for us because we're talking to industries that we've never interacted with either, so it's an opportunity for them to learn from us and us to them. But I think sometimes that's overlooked. We'll sometimes assume, that certain things are understood by everybody. We do have to back up and go through those. How is that approached and handled to make sure that, people that are wanting to benefit from this type of technology have a better understanding of how it works?
that's big. I tell customers a lot, we're not just, making tools out of 3D printing, which we are, but we're introducing new materials to the tooling market that they've never used before. Dave, you're absolutely right that people don't know these tools and how they're going to react. That's why they ask longevity, durability, and all these other questions. They don't know.
So I think that kind of wraps up our session. If you look at the back of your name tag, it'll tell you if you're going to the materials technology or the machine technology next. So we'll kind of, if we've worked it out right, we should be, kind of make something out of the group a little bit. So thank you all for your contribution.